Now we are going to take a look at chiral molecules with more than one stereocenters. We've seen some examples before. Now we are going to take a look at them systematically. So here is an example. This is a molecule with two chiral centers. All right. We will number the carbon chain starting from the right-hand side. It's a carboxylic acid, and we will talk about this next semester. But the carboxylic acid group takes the highest priority. Anyway, so the chiral center is at carbon 2 and carbon 3. So let's do some stuff just on theory. So imagine we have two chiral centers. Suppose the first molecule has the R and R configuration as both chiral centers. So I put down 2R, 3R as its chiral absolute configuration. The next molecule could have 2s, 3s, with both chiral centers opposite to the previous one, right? These two compounds will be enantiomers of each other because they have both chiral centers opposite to each other. They are going to be mirror images of each other, and they will not be superimposable. Okay? The third molecule, what we can do is to change one chiral center but leave the other the same. For example, we will keep the chiral center carbon 2 as R and change the chiral center at carbon 3 to S. Okay, now we have 2R, 3S. And lastly, for the last molecule, we can do the opposite, 2S, 3R. Now, if you take a look at molecule 3 and 4, you see at carbon 2, the configurations are the opposite. One is R, one is S. Carbon 3, opposite. One is S, the other is R. So both chiral centers in carbon 3 and 4 are opposite to each other. As a result, 3 and 4 are also enantiomers of each other. Okay, so now we have two pairs of enantiomers, right? But what is the relationship between, let's say, 1 and 3? Molecule 1 and molecule 3. We have 2R, 3R and 2R, 3S. So one chiral center has the same configuration. The other chiral center has a different configuration. So we have a different term to describe them. They are called diastereomers. Diastereomers are stereoisomers that are not related as an object and its mirror image. Okay. They are stereoisomers for sure. They have the same formula, they have the same constitution. It's just the arrangement of the substituent in space that is different. And in this particular case, carbon 3 has different arrangement of substituents, right? Basically, enantiomers are not, diastereomers are stereoisomers that are not enantiomers. Okay, they are not mirror images, but they are still stereoisomers of each other. Okay, so same thing is for molecule 1 to 4, molecule 2 to 3, molecule 2 to 4. They are stereoisomers that are not enantiomers, so their relationship will be diastereomers. For molecules with more than one chiral centers, if one or more chiral centers have the same configuration, one or more chiral centers have different configuration, they are diastereomers. Okay, and in our case here, two stereo centers. One is the same, the other is the opposite. Their relationship will be diastereomers. So with that being said, let's take a look at the molecules in Fischer projection. We have two chiral centers, so we are going to put two cross, and those two cross will be linked to each other. So carbon 1 is on the top, carbon 2, 3 are chiral, and carbon 4 at the bottom. This is the first molecule. We put both OH groups on the right-hand side. If you draw the mirror image of this molecule, the two OH groups will be on the left side. Okay, and here is the mirror. They are mirror images of each other. But this is Fischer projection. They are not exactly the same. Okay. The first molecule represents 2R, 3R. The second molecule represents 2S, 3S. Okay. So I want you to determine the R and S configuration at the chiral center on your own. Okay. So you need to get 2R, 3R from the left molecule, 2S, 3S for the right molecule. Always keep in mind, hydrogen is on horizontal line. Horizontal means the bond is coming toward you. So you always have to invert it in Fischer projection. All right. The next two molecules, the first one, we put carbon 2 OH on the right, carbon 3 OH on the left. And its enantiomer, they have the opposite configuration. Okay. And here is the mirror. They are mirror images of each other. The configurations are 2R, 3S, and 2S, 3R. Okay. So these are the four stereoisomers of this compound. As we have seen, the first two are enantiomers. The last two are enantiomers. They are mirror images, but not superimposable. And 1 and 3, 1 and 4, 2 and 3, 2 and 4 are diastereomers. Stereoisomers that are not enantiomers, that are not related as an object and its mirror image. One important aspect that I want to point out here is that diastereomers have quite different physical and chemical properties, which means they may have different polarity. They may have different solubility in solvent. Okay, so diastereomers are different molecules that can be separated. enantiomers cannot be separated directly. Okay, we will revisit this concept later. All right, now let's take another type of molecule. With two stereocenters, we can have achiral molecules. So let's see this example here. Instead of having a carboxylic acid, we have two methyls at the end. Okay. Now let's draw the Fischer projection for the stereoisomers for this compound. The first one, I put OH, the two OH groups on the opposite side in the Fischer projection. And if we draw the mirror image of it, here's what we get. Okay, the mirror is in the middle. And the third one, I can put the OH groups on one side of the Fischer projection. All right. Now, for the stereocenter, first molecule 2R, 3R. Second molecule 2S, 3S. How about the third molecule? With what's being drawn here, the third molecule has 2S, 3R. And it has a plane of symmetry. The plane of symmetry right here. So the third molecule is the mesoform that we have talked about before. If you want to draw its mirror image, here is what we get. But the mirror image of the mesoform is superimposable onto itself. So if you turn the molecule in the plane 180 degrees, you see how they overlap. Always keep in mind, Fischer projection, horizontal lines are coming towards you. When you turn the molecule, we are not changing the horizontal line, but we put the top carbon at the bottom, bottom carbon to the top. Okay, so the left side OH now will be on the right hand side. But basically we put the molecule upside down and they overlap with each other, right? This is the mesoform with a plane of symmetry. They are not enantiomers. These two forms are identical. Okay? But for the first two pairs, we have enantiomers, mirror images, but not superimposable. Alright? The middle form, these two are identical. Alright, now my question to you is, what is the relationship of the first molecule to the middle form? Or the second molecule to the middle form? What's the relationship? They have one chiral center the same, the other chiral center the opposite. Right? So, diastereomers. Okay. The middle form is a diastereomer to the pair of enantiomers. Okay? So, as for practice, I want you to try these molecules. So what's being shown here are 4 stereoisomers of a cyclic compound. There should be two pairs of enantiomers, right? So this represents the chiral molecule with 2 stereocenters. So determine the chiral center, absolute configuration at the chiral centers, and try to see the relationship of these molecules. And the second set, I put down another 3 molecules. These are examples of achiral molecules with 2 stereo centers. I mean the first one at least. The first molecule is an achiral center with 2 stereo centers. The other 2 are still chiral. They are a pair of enantiomers. So determine the R or the S configuration for each of the chiral center and try to look at their relationship to each other. Okay? And so here is the answer to the absolute configuration. But you need to work this out yourself. All right? Okay. Lastly, we will take a look at molecules with multiple stereo centers. Yeah. More than 2 stereo centers. The maximum number of the stereoisomers for a particular constitution is 2 to the power of n. N here is the number of stereo centers. So for example, here is the structure of glucose, a carbohydrate that is most abundant in our body. This is D-glucose. It has 6 carbon atoms with 4 chiral centers. All right. Now, if we use the formula to calculate the number of stereoisomers, we have 2 to the power of 4, which equals to 16. So there are 16 stereoisomers to D-glucose. So if you are interested, you can find the structure of all 16 stereoisomers in Chapter 25, the chapter on carbohydrates. All right. Now 2 to the power of n, that's the maximum number of stereoisomers for a constitution. When 2 or more stereo centers are equally substituted, mesoforms are possible. Then the number of stereoisomers will be less than 2 to the power of n. In our previous example, for molecules with 2 stereo centers, you've seen that if 2 stereo centers are not equally substituted, we have 4 stereoisomers. That's 2 to the power of 2, 4 stereoisomers. But when the mesoform is possible, we only have 3 stereoisomers, right? So in that case, the chiral carbons are equivalently substituted. Both chiral carbons have the same groups attached to them, and the mesoform is generated, and the number of stereoisomers is less than 4 in that case. All right. Lastly, I want you to take a look at this example here. A 5-carbon molecule with some chiral centers. I'll let you determine how many chiral carbons are there and how many stereoisomers are possible. Okay, So we will check our answer in class.